We are working on applications of higher order derivatives. The example that we are working on is the concentration of a drug in a patient's bloodstream when they are given an oral painkiller. We have computed part A, which is the rate of the drug in their bloodstream. We have computed part B, which is the rate of this painkiller. And now we're going to move on to part C. Part C asks, at what rate is the concentration of the drug changing after 1 hour? Is the concentration changing at an increasing or decreasing rate at this time? So, since it's just talking about rate here, that means we're going to use our first derivative, r prime of t. We computed that in part A, so let me go ahead and pull that up. So I have my rate equation listed here. If we want to know what's happening to it after 1 hour, then we just need to substitute 1 in for our variable of t. So we're looking for the rate at 1 hour. Now I can plug it into either version of this format, whichever seems easier to you, and I'm going to go ahead and plug it into my factored form. I think it might be a little easier. So I have negative 5 times 8 times 1 squared minus 9 over 8 times 1 squared plus 9 quantity squared. So in the numerator, I have negative 5 times a negative 1. And in the denominator, I have 17 squared. And so that simplifies to be positive 5 over 289. Since this is an applied problem, we might want to figure out what this is approximately. And so my decimal approximation for this is 0.0173. Okay, so what did we actually compute here? This is my rate equation, which is a derivative. So I need something per something. Well, my first one is the concentration of the drug to be exact, and what I'm comparing it to with respect to time. So in this case, my concentration of the drug per hour. And so this is my answer here. The second question asks, is the concentration changing at an increasing or a decreasing rate? Well, we just need to look and see whether my answer is positive or negative. This came up to be a positive answer here, and so therefore my concentration of this drug is increasing at this time. So the blood is absorbing more of the drug at this time. I'm going to go ahead and double check this answer by using my calculator, and that's going to help me with my next part, part D as well. So I have my equation plugged in of 5x over 8x squared plus 9. Let's graph this on the standard window, so zoom 6. We see everything is centered around my x-axis here, so let's go ahead and zoom in on that. So I need to minimize my y value, so let me just do my y min of negative 1, my y max of positive 1, and then I'll go by my scale of 1/10 or 0.1. So I can see this here. We also know that this is an applied problem, so we don't really want to talk about negative time. So something else that we could have adjusted is we could let our x value be virtually just positive. I'm going to go ahead and select a negative value here so we can see my y-axis on my graph. And so here's where we're focusing. If we want the rate after 1 hour, then we can use the calculator to double check that. We do second trace to select our calculate feature. Option 6 gives us the rate, and we push in 1 because that's when we want to look at after 1 hour. We can see that we have the right derivative here, 0.0173, and so we have the right answer. Now, the main reason that I wanted to look at this on the calculator is to help us with part D. So let's go ahead and move on to that. Part D says, when does the concentration of the drug begin to decline? Well, we know when we're talking about our rate equation, that really gives us slope, rate of change, velocity, so on and so forth. Let me talk about slope here because I'm going to apply this to the graph. I know that if my slope is positive, then my rate of the equation is positive. Therefore, my slope of my graph is increasing. If the slope of my graph is negative, then the rate of my graph is negative, and therefore the slope of my graph is decreasing. So my rate equation and slope are the same thing. So over here, my rate is increasing as long as my graph is increasing, and over here my rate is decreasing where my graph is decreasing. If we want to talk about when the concentration of the drug begins to decline, notice that's going to happen up here at the peak of my graph when I switch from increasing to decreasing, or when my slope or when my rate equation is equal to 0. So if we ever want to see increasing and decreasing, we're going to use the derivative equation. I want to know where this is increasing and decreasing, so I use my derivative equation, which is given by my R of t in this problem. So I do that by figuring out when my slope is equal to 0. That's going to give me my peak of my graph. If I look at my graph, I can see that my peak of my graph is right around here. So my answer should be right around here, and that should be very close to my 1 value. So we know what answer I'm looking for before I even actually get it. Okay, I'm going to take my rate equation. Again, we did it from part A. So I'm just pasting it from part A, and I want to know, when does this equation equal to 0? Now, I'm going to use my factored format, so let me get rid of this version here, but we know it's the same thing. I know I can get rid of the denominator by just multiplying by it, so let me cancel that out. I know that this -5 is not going to apply, because if I set it equal to 0, that also cancels out. So really, this is only going to apply when 8t squared minus 9 is equal to 0. If I move my 9 over to the other side and divide by 8, I get t squared is equal to 9/8. To get rid of the square, I force in a square root, which really means I have to force in a plus or minus. But this is an applied problem. We're talking about the time, so we're just going to look at the positive version of this. Let me simplify this a little bit. The square root of 9 gives me 3. I can also simplify the square root of 8. I can break down it as a square root of 4 times square root of 2, so that gives me 2 root 2. So my exact answer here is, when does my concentration begin to decline, is this value here. But again, this is an applied problem, so we want to actually know, when is this actually happening. If I were to figure out my decimal approximation for this, it would be 1.0607, and since my variable is in time, then this is hours. So our rate begins to decline at 1.0607 hours, so shortly after 1 hour. We can confirm that again on our calculator by looking at the max, so second trace to get my calculate feature. Option 4 gives me max. I go somewhere left of where I think my maximum value is for my left bound. For my right bound, I go somewhere right of where I think my maximum is. I guess to where I think my maximum point is at. And we can see that that happens right here at 1.0607 if I were to round it up to 4 decimal places. And so this tells us where our concentration begins to decline. And so now we have finished up part C and part D of our painkiller example.